Okay? So remember, the sample is not the target. The sample is what is being irradiated. This is being bombed by the electrons in the tube. Copper target in X-ray tube. Okay? And that means that the lambda of the radiation is lambda copper, and I'm going to use lambda copper K alpha because I know its wavelength to 5 significant figures. It's 1.5418 angstroms. And here's the data set. I looked this up in the literature. So here's the data set from the experiment. And that's all you get, a set of 2 thetas. So here's my challenge to you. I'm telling you, you've got an unknown sample that's cubic, and there's your data set. The task for you is determine 2 parts to the question. And we're going to do it together. First part, determine the crystal structure. So it's either FCC, BCC, or simple cubic. Determine crystal structure. And the second part is determine the lattice constant, the value of the lattice constant. So you can get quantitative measurements. So I'm going to show you how to do it. So how are we going to do it? We're going to use this technique. This is my self-help book for you. All right? And here's the key. Here's how I came up with this. There's a way to unravel this. And the way you unravel this is to take these 2 relationships. You have lambda equals 2d sine theta is 1. And you also know that d, in fact, I'm going to keep writing HKL subscripts here. You know that d HKL is equal to A. That's this lattice constant. Be sure, this is lattice constant. This is the cube edge measurement, lattice constant, divided by the square root of h squared plus k squared plus L squared. So what I do is I combine the 2. If you combine these 2, you can end up with this relationship. If you combine the 2, you get lambda squared over 4a squared equals sine squared theta over h squared plus k squared plus L squared. And this is the key. Why is it the key? The value of lambda is set by you. You chose the target. The value of A is set by the sample. That's the lattice constant. So the ratio of 2 constants is a constant. Agreed? So this is constant. So if the left side of the equation is a constant, the right side of the equation must be a constant. But h, k, and L vary, and theta varies. But the ratio of the variation when mapped into sine squared theta over h squared plus k squared plus L squared, this must be a constant. And that's going to be the way I work through this delightful problem. So let's see. Start with 2 theta values and generate a set of sine squared theta values. That's what Sadoway says first. So I took 2 theta. All I did was make 1 theta and then took the sine of it and then took the square of the sine. So this is the data set transmogrified into sine squared theta. All right, what's the next thing he says? Normalize by dividing through with the first value. So I'm just going to take this whole series and divide it by 0.143. And now I end up, instead of 0.143, 0.191, I got 1, 1.34, and so on. So that's what I mean by normalize. Normalize to the first entry. Okay, what's the next thing he says? Clear fractions. Clear fractions from the normalized column. So I'm going to multiply this by a common number to get rid, because 1.34, remember, this is experimental data. It's noisy. 1.34 looks like 4/3, doesn't it? If you're fuzzy logic. And 2.67 looks like 2 2/3, 3 2/3. That's roughly 4, 5 1/3. The 3 looks like a magic number. So if I multiply this column by 3, I get 3, 4, 8, 11, 12. What's it say next? Speculate on the HKL values that, if expressed as h squared plus k squared plus L squared, would generate the sequence of the clear fractions column. And then that's going to take me to the selection rule. So I say, well, how do I get 3? It's 1 plus 1 plus 1. 4 is 2 squared plus 0 squared plus 0 squared. 8 is 2 squared plus 2 squared plus 0 squared. So I'm generating this thing. And now it's pretty obvious, right? Because now I've got to use these. And what do I see here? Well, 1, 1, 1 are all odd. 2, 0, 0, all even. 220, all even. Gee, this looks like it conforms to the selection rules for Bragg reflection from an FCC crystal. Right? And then to make sure that I'm onto something, what I do is this. Compute for each theta the value of sine squared theta over h squared plus k squared plus l squared on the basis of those assumed values. What I'm doing is I'm saying, if my hunch is right, whatever I choose for the theta and the assumed value of h squared plus k squared plus l squared, that should be a constant that doesn't change. So let's test it. And sure enough, look, 0477, 0478. So it looks like I'm onto something. And furthermore, I know what this is. That 0477 is this, right? This is 0.0477. And I know my lambda, that's 1.5418, so now I can calculate my A. So now I've determined that it's FCC, plus if I go ahead and I calculate the A value, I get 3.53 angstroms. And if it's FCC and it's 3.53 angstroms, I bet it's nickel.